Hi everyone. So this is the computational demonstration for the Bayesian methods that we've just been talking about. So the first demonstration is really the example 4.1, which is the coin flip, the Bernoulli trials. And the idea here is to kind of show how the posterior changes as a function of number of data points considered. Now remember, in this coin flip example, we have our goal is to estimate the probability of heads, and and consider sort of how that probability of heads changes as a function of the number of data points considered. So let's start off by generating some synthetic data. So I'll start off with a probability of success, or the probability of heads, as being 0.5, and I will generate 200 data points. Then what I do here, because I always like to define sort of my parameters at the top of my code, even if mathematically it makes me sort of jump around in logic, is to sort of define the hyperparameters for my prior. And just like in the example, I'm going to consider beta prior. And those hyperparameters need to be greater than 0. So I'll select them as being 4 and 3. And we can look at sort of what the effect of the hyperparameters is later. Then I will start generating my synthetic data, and I will generate 200 samples. Now I'm going to do something interesting here. And this is sort of, we need to pay a little bit of attention because this is different from the example. I'm going to consider, after every coin flip, the total number of counts of heads and the total number of counts of tails. After the first coin flip, after the second coin flip, after the third coin flip, and so forth. Why do I do that? Well, because I want to build a posterior after one coin flip, a posterior after two coin flips, and so forth. And I know that my posterior depends on my accumulated count up to that point. So that's why I need to consider sort of the cumulative sum of heads and the cumulative sum of tails. I call these sort of ones and zeros by convention. The rest, honestly, is just plotting. So before we do that, we need to define the alpha tilde and the beta tilde for my posterior. So in my posterior, I have the cumulative sum of ones plus alpha, and my beta tilde is the cumulative sum of zeros plus the beta from my prior distribution, my beta distribution. So remember, my beta distribution is conjugate to my Bernoulli. So the alpha and the beta, which are the hyperparameters of my beta distribution, are going to, when multiplied by the likelihood, going to become alpha tilde and beta tilde. Once I have defined the parameters for my posterior, then I can go ahead and plot my beta distribution for each one of my successive coin flips. And the rest is plotting. So I've outputted sort of my 200 numbers that I've generated. So the first time I flipped a coin, I got tails, then I got heads, then I got tails, tails, and then I got heads. I'm plotting the cumulative sum of ones and the cumulative sum of zeros, right? So here I have not yet accumulated a one, so it's still just heads. Then I've accumulated, or it's still a zero. Then I've accumulated one, so now that becomes a 1 until I get another 1, and then that becomes 2, and so forth. So those are the parameters that are going to inform my posterior obtained at the various draws. And then finally, I plot that posterior. So this is a complicated looking graph. In fact, it has 200 curves superposed. The first curve, the one on the leftmost here that I'm pointing to, is the prior. But then as I start collecting more and more data, something kind of beautiful happens. It starts centering itself, and the posterior starts getting sharper and sharper at 0.5, which was the ground truth value for the probability of flipping heads. So I think what's kind of interesting here is the fact that I start off with a prior, which is kind of broad, and then eventually it sharpens to something which is very closely centered at 0.5. We can repeat this exercise, for example, to make it a little bit less messy, with 10 draws, and maybe choose hyperparameters here which are, let's make it 1 and 2, and then kind of look at what this will look like. So right now the code is still running. And here we are. That's interesting. So the prior itself looked quite different prior to the collection of more data points, but eventually it starts again kind of sharpening at 0.5, but not really. It hasn't had enough data in order to be able to sharpen there. Again, I can choose different hyperparameters, let's say 5 and 5, and then keep it at 10. And my prior sort of, at this point looks a little bit different. It looks more like a, it looks more like a function which is centered at some value. In this particular case, it was probably centered here. And then what I'm recovering is eventually after 10 data points, something which is centered at closer to 0.5. So let's go back and set this to, let's say, forget what it was. I think it was 2 and 3 or 2 and 4, something like that. And set this to 100, not quite the 200 it was earlier. But there we go. I mean, we have a prior which is kind of broad and eventually is sharpening as we accumulate more and more data in our successive posteriors. So, I encourage you to sort of play around with this for yourselves and look at sort of the effects of the prior and look at the effects of the number of data points in sharpening the posterior. And by the way, you don't necessarily need to start off with 0.5. That's another thing we can move or change. We can make the ground truth 0.8, and so eventually we should obtain a posterior which is much more sharply centered at 0.8, exactly as we'd expect. So let's move this back to 0.5, because looking at a coin flip with 0.8 might confuse people looking at it the first time. Let's look at another example and sort of our last example. This one here is example 4.4. We kind of did the math of it over the course of our lectures, and we sort of looked at the prior that was conjugate to the Poisson distribution. That prior conjugate to the Poisson was the gamma distribution. And we'll be following a pattern very similar to the one that we just followed in the previous example. So in other words, we will generate our synthetic data. Here we will basically say that the mean of the Poisson distribution, or the parameter, the numerical value for the parameter of the Poisson is going to be 5. And we're going to generate our data according to Poisson distribution with mu is equal to 5. And we're going to generate 20 data points. And again, because I like putting all my parameters that I specify at the top, even if mathematically it makes us sort of logically jump around a little bit, I will define 2 hyperparameters for my gamma distribution, the shape parameter and the scale parameter, and here I've set them to 1.5 and 1. I just have to remember that they need to be, or they need to stay greater than 0. Then I'm going to draw samples from my Poisson distribution, and remember, because I'm going to want to plot successive posteriors, that I'm going to be taking the cumulative sum of my samples, which are going to be required in order to be able to plot my posterior gamma distribution. And then finally, the rest is pretty much the same as the previous example. I have to find sort of the successive values for the parameters of my gamma distribution as I collect more and more data, and then eventually just plot my resulting gamma distribution. And it's something that looks like this that we obtain. So notice, by the way, for the beta distribution, the example that we were looking at earlier, the probability of heads was between 0 and 1, and the beta distribution did not allow me to explore a support beyond 1. The gamma distribution is a distribution which has support from 0 to infinity. Presumably, this blue curve here is my prior. I've collected 1 data point, and I get closer and closer to the theoretical value, which in this particular case is 5. We can go ahead and try it out for something different. We can make it a mu of 15, and we could increase the number of samples, and now we can run it. So we expect, again, for the distribution to be centered at 15. Oops, and it's plotting here from, I want to plot it from not just 0 to 10, but maybe 0 to 30. And here we are. We're finding something which is very sharply peaked, or is becoming increasingly sharply peaked at 15. The prior started us off here, and then we started evolving in this particular direction. So hopefully this gives you an idea for how Bayesian methods work. We start off with some kind of prior distribution, which is pretty flat, and then start collecting an increasing amount of data. Well, not just pretty flat, but it's pretty flat in the region where the posterior ends up having a peak, is what I meant to say. And then as we start collecting more and more data, then the posterior eventually sharpens at this particular value, which we had selected to be 15. So again, hopefully these examples are useful to you. There's a couple more examples, I think, for chapter 4, but those pertain to sort of the advanced section. Maybe if I can highlight just one of them in case you'd like to read that advanced section. It's one where we identify sort of change points in data. So where we identify kind of where the data change statistics. So if you imagine that you have data and that data shows steps and you'd like to be able to find where those steps are, how do you go about doing it? So we developed, or we wrote code for implementing a method for identifying where these change point locations are. And what's pretty cool is that sometimes you can identify change point locations in regions where it isn't even obvious by eye that you have a change point, but rather these methods can sort of detect them and find them pretty straightforwardly based on sort of violations of expected statistics. All right, so with that said, thank you, and have fun exploring.